This is lecture 18. Today we'll be talking about molecular orbital theory. So this is just about the best theory we have in chemistry. It basically describes everything we need it to. So this was developed by an American chemist named Robert Mulliken. And what Mulliken said was, in molecules, electrons don't really belong to atoms anymore. They really belong to the group. He also said that molecular orbitals are delocalized over the entire molecule. So we've talked a little bit about delocalization in terms of double bonds, and we're still going to kind of use that terminology sometimes, but really it turns out that all molecular orbitals are distributed over vast regions of the molecule. So the molecular orbital is the 3D standing wave, right, that's describing where the electron is going to be 90% of the time. So we're not actually changing a lot of definitions here. The molecular orbital is similar to an atomic orbital in a lot of ways, except its shape is very different. But we are going to introduce a few new terms today. So let's start actually with some familiar terms, or well, I guess maybe new right off the bat, but we have what's called a bonding orbital in molecular orbital theory. This bonding orbital is low in energy. So right here on the left, I have a diagram where the x-axis here is just the distance between two nuclei, and the left axis is the potential energy. And right here, this bottom line represents the potential energy for this bonding orbital. There's some minimum distance where you have the nuclei, where you get a very stable bonding orbital. And when you get this bonding orbital, you get an increase in electron density between the nuclei. So what I'm showing in this plot is another, so you'll see I have two nuclei on the bottom. So this is distance on the bottom. And on the y-axis, we're looking at electron density. So in this bonding orbital, we have a lot of electron density here. Now, a term that's going to be very new to you is the antibonding orbital. So the antibonding orbital's potential is actually shown on this left plot as well. And as you can see, it actually never has a negative potential. It's always positive, which means it's not favorable to have. So in molecular orbital theory, we have orbitals, these bonding orbitals, which are orbitals that are beneficial to have, and we have these anti-bonding orbitals that are not beneficial. They're detrimental to having a stable molecule. And in these anti-bonding orbitals, we tend to think of the density in between the nuclei as being decreased. There's some point where the density actually goes to zero. So we actually get a node between the nuclei. So the idea here is we take two regular orbitals, these could be s orbitals, and we're going to combine them. So we're going to get, when we combine them, we're going to get a bonding orbital and an anti-bonding orbital. You'll notice we're still starting with two orbitals, and we're still ending with two orbitals. In this bonding orbital, if we look at this as a function of energy, the bonding orbital is significantly lower in energy than the atomic orbitals. In contrast, the anti-bonding orbital is higher in energy than the atomic orbitals. So that's why it's favorable to be in a bonding orbital, not favorable to be in an anti-bonding orbital. And that's the basics of it. We'll spend the rest of this time getting much more complicated with it. But the good news about molecular orbital theory is it basically gives us everything we need. It describes all molecular properties that we can think of. So it describes bond energies, absorption, emission, spectra, polarity, magnetism, charge distribution. We can use it to determine the chemistry of molecules before they're even made. The bad news is that it takes, or that you get a unique set of molecular orbitals for each molecule. So basically, each molecule has orbitals that look different from every other molecule, right? Some can look very similar, but it's like a fingerprint. They're all going to be different at least a little bit. And additionally, you're going to need a computer to really calculate the molecular orbitals and energies. So even though this theory can be powerful and predict a lot of stuff, it takes a lot of computing power and can actually be very slow in getting results from this theory. I'm also going to give you a little bit of a warning that valence bond theory and molecular orbital theory actually use the same terminology for different things. So in valence bond theory, we use these terms sigma and pi to refer to bonds, whereas in molecular orbital, sigma and pi are orbitals. Right, so there's a bit of a difference there. So let's look at an actual molecular orbital diagram for H2. So here we're starting with a 1s orbital on each, and those are going to combine to give us a sigma 1s bonding orbital and a sigma 1s anti-bonding orbital. And we denote the anti-bonding, it's kind of hard to see on this slide, but we denote it with an asterisk. So if we think about electrons, if each of these hydrogens is starting with a single electron, when they bond here in the middle, we're going to put those electrons at the bottom. We're going to fill these molecular orbitals from the bottom towards the top. And so the highest orbital with electrons in it is we're going to call the highest occupied molecular orbital, right? So this is a new term for you, describing where the electrons go. It's the HOMO. And then the other term I'm going to introduce to you here is the LUMO, the lowest unoccupied molecular orbital. So this idea of HOMO and LUMO, the HOMO is always right below the LUMO. They're always right next to each other. Right, so you always think of that as a pair. The HOMO is kind of a measure of how full your molecular orbitals are, and your LUMO just tells you where the next open one is. All right, so far what I've been talking about are these sigma orbitals. You don't really know what what a sigma orbital really is yet, but in a sigma orbital you can have 2 electrons. And just like in every other orbital you've seen, every orbital, we're going to have 2 electrons filling it. And like I said, you're going to fill the lowest first. And we have these 2 kinds of bonds, the bonding and anti-bonding. And the difference is the node that's going right here in the middle. And that's really what's going to set these apart. But what we really want to think about too, in terms of these molecular orbitals, is our bond order. So with this idea where we have just these weird new diagrams, every molecule has its own molecular orbitals. They're all distributed in different ways. The bond order is not going to be as easy to figure out as just looking at a Lewis structure and counting bonds and resonance structures. But it's actually not super complicated either. In molecular orbital theory, we count the bond order as this. We take the number of bonding electrons, or in other words, electrons in bonding orbitals, and we subtract the number of electrons in anti-bonding orbitals, and then we divide that number by 2, right? We divide it by 2 because each orbital can hold 2 electrons. So in this case, for H2, we would have 2 electrons in bonding orbitals, 0 in anti-bonding orbitals. So we get 2 minus 0 over 2 equals 1 bond order. So we have a bond order of 1 in this case. And this molecular orbital theory can actually be used now to explain the absorption and emission of molecules. And this actually works the exact same way that it did for atoms. All that's happening is an electron can jump from a lower energy level to a higher by absorbing a photon of light. And the photon has to have an energy equal to the difference in energy of the 2 orbitals. And an electron can be emitted by a molecule a photon can be emitted by an electron dropping or relaxing to a lower molecular orbit. Now let's look at helium now. Let's compare its molecular orbitals and its bond order to that of hydrogen. So helium actually has a similar molecular orbital pattern in that we have this sigma 1s and sigma star 1s orbitals here. But how many electrons does it have? Well, each helium is going to be coming with 2 electrons. And so when those get put into the molecular orbitals, you're going to put 2 electrons in the bonding, 2 in the antibonding orbitals. What that means is when we calculate our bond order, we're going to have 2 bonding electrons minus 2 antibonding electrons divided by 2, which equals 0. So if you have a bond order of 0 between 2 atoms, you get an unstable molecule, one that's just going to fall apart. So the reason helium-2 doesn't form, we've talked a lot about filled valence shells, we've talked about bonding and expanded octets. The real reason helium-2 doesn't form is because for it to form, you'd have to have 2 electrons in bonding orbitals and 2 in antibonding orbitals. And since we have an equal amount of antibonding and bonding, you have 0 bonding. So in other words, there's no net gain for the 2 helium atoms to be together. Let's take this up a notch and look at a molecule that's coming in with 3 electrons from each of its atoms. So this would be lithium-2 or dilithium. It's supposedly what powers the Enterprise on Star Trek. But in each of these lithiums, we're going to have an electron configuration of 1s2, 2s1. So when we put those electrons into our box electron configuration, we'll have 2 electrons in 1s orbital and then 1 in a 2s orbital. Now you'll notice for this molecular orbital diagram now, we have molecular orbitals derived from the n=1 shell, and we have molecular orbitals derived from the n=2 shell, in this case from the s subshell. So we're coming in with 4 orbitals, we're coming out with 4 orbitals, but now we have a different order of the orbitals. So now these electrons that are coming from the atoms that are being bonded, we're going to fill those into the molecular orbitals with the lowest orbitals first. And now what you can see is at the 1s level, or at the n=1 level, you have a bonding and an anti-bonding arrangement. So for these, what we consider core electrons, there's actually no net gain from becoming a molecule. But with these valence electrons, we have electrons in bonding orbitals and none in antibonding orbitals. Which means that we can still kind of think of the valence electrons as doing all of the work and making this a favorable arrangement. Now let's think about these orbitals and think about what they look like. Okay, so the sigma 1s orbital, in a lot of molecules, this will just look like a sphere. But that's really only in diatomic molecules. Once you have 3 or more atoms, these all look fairly different. But the antibonding orbital looks like the bonding orbital, but with a node right down the middle. The sigma 2s orbital looks similar to the 1s or the sigma 1s orbital, except now we have this radial node that divides it into 3 parts. But you'll notice the electron density, there's still electron density right in the middle of the 2 nuclei. And then in the antibonding orbital up here, we're going to get a division in between the nuclei. We're going to get a change in phase for these guys. And we still have that radial node up here, right? So there's still nodes and so forth in these orbitals. And really, I'm going to teach you how to tell the difference between these sigma orbitals and what we call pi orbitals. So pi orbitals are largely derived from p atomic orbitals. That's not entirely accurate, but it's okay for today. So if we come in with 3 2p orbitals from each atom, then we're going to need to end up with 6 molecular orbitals. So what that's going to actually look like is we're going to get 2 sigma orbitals, a bonding and an anti-bonding orbital, and then 4 of what are called pi orbitals. So we'll get 2 bonding pi orbitals and 2 anti-bonding pi orbitals. Right? Now, the orbitals right here, the way I've arranged them energetically, this ordering actually depends on the specific molecule. So sometimes the pi orbitals will be lower in energy than the sigma orbitals. Sometimes you'll have an order that goes sigma, pi, pi star, sigma star, or you'll go pi, sigma, sigma star, pi star. So these orbitals can actually be in fairly different orders. So we'll have to give you the actual molecular orbital diagram. So you don't actually even have to come up with this. But let's talk about what these orbitals are looking like. So for the sigma 2p orbital, you'll notice we have nodes on the nuclei, but not in between them. So they are sharing electron density between them. But for the anti-bonding version of this, we have a node in between the two nuclei. We still have our nodes on the nuclei, but it's that node right in between that we really care about. Now, for the sigma orbitals, we have electron density between the nuclei, but for pi orbitals, similar to pi bonds that we were seeing in valence bond theory, the pi orbitals have density above and below the nuclei. So there's a node that runs through both nuclei here. And in the anti-bonding pi orbital, we still have that node that runs through the nuclei, and then we have one that runs between them. And of course, the other pi bonding and anti-bonding orbitals look the same as these first two. They are just rotated 90 degrees. So you think of these as being perpendicular to the other bonds. All right, so let's spend a little bit more time looking at these pi-type molecular orbitals. So here I have a simple pi bonding and a simple pi anti-bonding orbital. These both have this node along the intermolecular axis, or in other words, there's a node that is formed by drawing a straight line through both nuclei. So that's true for bonding and anti-bonding. The big difference is in anti-bonding, you get a node that's also perpendicular to the nuclei. So this symbol right here means that you have a line and then another line drawn through it. That means perpendicular. So this line right here is perpendicular to the node running through the nuclei. So all anti-bonding orbitals have this perpendicular node that goes in between the two atoms, the two nuclei. So this is true for sigma anti-bonding orbitals and for pi anti-bonding orbitals. And then the way you're going to tell whether these are sigma or pi is just by whether or not they have a node along the axis of the molecule. So a node that's running through the two nuclei here. So fortunately, with molecular orbital theory, you only have to figure out two basic nodes. You have to figure out the anti-bonding node and the node that separates sigma and pi orbitals. Let's give you a little bit of practice with this, and I want you to look at this diatomic molecule right here, and I want you to tell me if this orbital I have drawn is a sigma or pi orbital. So you'll notice that it's got red, and green. So all of that is single orbital. Go ahead and pause the video and try and figure this out. All right, so this has a node running through the nuclei here, right? It's separating the top from the bottom. So this would be a pi orbital. Pi means that it's been cut in half, the top and the bottom. Next question, is this a bonding or an anti-bonding orbital? Go ahead and pause the video right there and try and figure it out. All right, well, we have a node along the axis of the molecules or running through the two nuclei, but we don't have one between the nuclei. We don't have a node here that's splitting these in half, which means that this is going to be a bonding orbital. Let me show you a bigger molecular orbital diagram for oxygen here. So here for O2, right, for O2, we come in with a bunch of valence electrons in the in the n equals 2 state. We've got 2 in 2s orbitals, and then we've got 4 in 2p orbitals. right? So we've got the three 2p orbitals, the 2px, 2py, 2pz. When these two atoms come together, they form all these bonding and anti-bonding orbitals. And you'll actually notice here that we're starting with the n equals 2 level. With the n equals 1 step, we're actually leaving that off, because we usually are just worried about our valence stuff going on here. But what you're going to do here, when you see a diagram like this, what you're going to do is you're going to count the electrons, the valence electrons from both atoms, right? So this is what you've been doing all semester so far, figuring out how many valence electrons each atom is coming with. And then you're just going to fill this molecular orbital diagram from bottom to top, right? So in this case, since we're just dealing with the n equals 2 molecular orbitals, we're just worried about valence electrons. So you're not going to count all the electrons that these are coming with, just valence electrons. And as you're filling these, you'll notice that up here at the top, when we've got some degenerate molecular orbitals, we'll pair these off singly before they get coupled together. So this is just Hund's rule, or the Pauli exclude, or yeah, so this is just Hund's rule that says these guys all want to be alone if they can. Now, if I was going to give you a diagram like this, I could ask you, where's my HOMO? Which orbital corresponds to my HOMO? And of course, your HOMO is your highest occupied molecular orbital. So that would be your pi antibonding orbital right here. And if I asked you, where is your LUMO? Your LUMO is always going to be right above your HOMO. It's going to be this sigma antibonding orbital. All right, let's see how you're dealing with all of this information. And I want you to give me the MO diagram of, or sorry, I've got the MO diagram of O2 shown here. And I want you to just simply give me the bond order here. Go ahead and pause the video and try and figure this out if you need to. All right, so what we're going to do, so we're going to take the bond, or to calculate the bond order, we're just going to find the bonding electrons in here, subtract the anti-bonding electrons, and divide by 2. So I see 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons, and I see 4 anti-bonding electrons. So how did I figure out which were bonding, which were anti-bonding? Well, all the anti-bonding ones are in orbitals denoted with this asterisk. So any electrons next to a label with an asterisk are anti-bonding orbitals. So here I have 8 bonding minus 4 anti-bonding electrons. I'm going to divide that by 2. And so my answer here should be 2. So that's for O2. But now let's look at O2 minus. So O2 minus is what's known as superoxide, and it's deadly. Your immune system actually uses O2 minus to kill invading microorganisms, but it actually hurts the body by doing this. But in this practice, I want you to actually fill in the molecular orbital diagram for O2 minus, and then I want you to figure out the bond order for it. So go ahead and pause the video now if you need to and figure this out. All right, so in this case, each of these oxygens is still coming in with 6 valence electrons, which would be 12 electrons total, but we get this extra negative charge, so we get 13 electrons. So if we fill this from bottom to top, we're going to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 electrons. And now if we count our bonding electrons and subtract our anti-bonding electrons, I see 1, 2, 3, 4, 5, 6, 7, 8 electrons in bonding orbitals, 1, 2, 3, 4, 5 electrons in anti-bonding orbitals. So that's 8 minus 5 divided by 2. We actually get a bonding order of 1.5. So that is our answer. So by gaining additional electrons, the O2 molecule actually goes down in bonding order, right? So that's a reason why O2 would actually not want to be negatively charged. It would prefer to have less charge than that. All right, so if you can do that, you have a good start with molecular orbital theory. And we'll keep going with some applications of it in the next lecture. But we'll finish off here just talking about the magnetic properties of molecules and how we can use MO theory to figure that out. So if you remember, diamagnetic materials have all their electrons paired. So this is generally what we consider non-magnetic. And in paramagnetic materials, you have at least one unpaired electron. Confusing thing here is para. Sounds like it's talking about pairing, but para, in this case, for whatever reason, means unpaired. So just keep that in mind. Para does not mean paired for whatever reason. But let's look at the MO diagrams for N2 and for O2. So in N2, you'll notice that all of the electrons are paired, which means this is not paramagnetic, it's diamagnetic. But in O2, we actually have two unpaired electrons. So O2 is actually paramagnetic. So this means that oxygen is actually magnetic, whereas nitrogen is not. I'll give you a little bit of a video of that.
Nitrogen is not magnetic. It is diamagnetic. All the electrons in the molecule are paired. Oxygen, however, interacts with a magnetic field because it is paramagnetic. This physical property indicates that molecular oxygen has unpaired electrons. Molecular orbital theory accounts for this fact, but valence bond theory does not.
Now, one last thing I'll point out before we go is if you look at these molecules, their MO diagrams, you'll notice, I mentioned this a little before, but you'll notice their order of molecular orbitals is actually slightly different. In N2, the pi bonding orbitals are lower in energy than the sigma bonding orbitals, whereas in O2, the sigma bonding orbital is lower than the pi bonding orbitals. Every MO diagram is going to be a little bit different. Some of them are actually the same, but the energy spacings which we don't often show are going to be a little different. So we're generally going to have to give you the MO diagrams. All right, that's it for molecular orbital theory. Good luck in figuring this out. It is complicated, so make sure to be diligent in your studies.